we have come back to ring theory. Now this time with polynomial rings. Let us now recall from our school days that when we were first introduced to algebra, elementary algebra, we came across symbols that looked like this: minus x, 2 plus x, 3 minus x plus x square, x cube, etc. And in fact these symbols are the first things we encountered in elementary algebra, where we were told that this x is an unknown quantity. It has got some sort of an infamous status. X is something that you don't know in algebra. People jokingly say like that. We then gradually learned how to add such symbols, multiply any two of them, and in fact even dividing we learned how to divide one symbol by another such symbol, namely the synthetic division of polynomials. We have already gone through all these operations many times, so many times that in fact they have also become somewhat natural to us. When we in fact think of algebra, these are the symbols that first come to our minds. Then after having that initial introduction, somewhat later in our mathematical studies in college level, we again encountered polynomials, but now the polynomials appeared as functions, and we wanted to know their values, their maximum minimum values. We came across the fact that polynomials are always continuous functions. They can be differentiated and integrated. So those things, the calculus of polynomials, we saw those things. But now in this study of polynomials, we are not going to look at polynomials from these two perspectives. For us, polynomials will be elements of a ring, and we will be concerned about algebraic properties of that ring. So let us start by defining what polynomials are algebraically. The previous interpretations were x is, although it's an unknown, but we think of x always as a number. Now we will not follow that interpretation. For us now x will simply be not just an unknown but an indeterminate, which there is no need for you to know what x actually is. It's just an abstract symbol which is a part of those symbols that we are calling polynomials. So that's how we are going to present the definition like this. Let f be a field by the ring of polynomials in the indeterminate x over f. Over f, or in fact there is you can write over f, but since here we have the field f, it is fixed, so it is over f. Every polynomial is over f. What that actually means, it will be clear soon. Written as f, then within square brackets we have x, is the set of all symbols. By the ring of we mean the set of all symbols that look like this: a naught plus a1x etc. plus a n x to the power n, where n is any non-negative integer and the coefficients a naught, a1 etc. up to an are in the field F. It's the fact that the coefficients are coming from the field F. That fact is expressed by saying that the polynomial is a polynomial over F. Okay, when we say over F, it means that the coefficients are coming from the field F. In place of this F, you can have any field, either the field of real numbers or the field of complex numbers, or in fact you can have any finite field also. We have already come across finite fields. For example, you have this field with two elements, that also can be taken in place of F, so that here each ai is either 0 or 1. It's a field which has only two elements. One of them is the 0 element and the other is the unit element. Okay. We shall now simply saying that this set of all such symbols is a ring clearly is not justified until we show that it is in fact a ring, and for that we need to also say what the addition and multiplication are. Okay, so we shall now define equality, addition and multiplication in fx. Not only do we need the operations in fx, but we also need to show, say what it means for two elements of fx to be equal. That has to be defined first. But there is one very important and subtle aspect about this definition. We could have avoided the phrase this phrase set of all symbols. By appropriately using what is the exact apparatus of sequences by an of sequences. However, the current approach to call fx a set of symbols seems more familiar to most of us. Now these words are not something to be taken lightly. Okay, if you are really thinking about this phrase, the set of all symbols, it needs to be interpreted properly. You see, we have already discussed when as we are developing the real analysis in Terence-Tau, we have been doing it as logically as possible, starting from first principles. We are in fact in the process of constructing the number systems that we will be needing later on, and in doing so we are going as logically as possible. So in that sense, this actually is somewhat vague, this definition, simply because of the phrase set of all symbols. What do we exactly mean by set of symbols? You may think that we are simply wasting time on something that is clear. I mean, this is a symbol and we are considering the set of all symbols. But the thing here is that this symbol has many things in it as its components, which don't have different meanings on their own. For example, this plus is not actual addition. It's not meant, you should not interpret this as a sum of the symbols a0, a1x and so on up to anx to the power n. This is not an ordinary sum of numbers. Keep in mind that now in our interpretation, x is not a number, or in fact x is not a field element. X is actually nothing. X and its powers are placeholders. In fact, this x to the power n does not mean, at least for now, x times x times x n times. That is not the meaning of x to the power n. This symbol on its own has a meaning. Its only meaning is that it's an abstract symbol where we have these parts x, these plus signs, etc., and powers of x, but they don't mean that these are ordinary operations of addition. And for example, here you have, it seems like we have the product of an and x to the power n, but it's not ordinary product because x to the power n is not an element in F, so that you can think of it as the product of these two elements in the field. X to the power n is not an element in the field, it's just a symbol, and these are all components of that symbol. The only things that are known to us or are coming from something that is already known to us are the coefficients which are coming from a field. We already know what a field is. So the symbol as a whole has meaning, but its individual parts separately don't have any meaning except the coefficients. They are elements of F. So you can understand that the whole thing has to be dealt with more carefully than we usually do. What we do in the interpretation where x is thought of as a number, 3 minus x plus, I think I need to. So I was saying that when you are say adding the polynomials 3 minus x and say 2 plus x square, just like you ordinarily carry out this multiplication, you don't even think of symbols or anything, you just simply do the computation as if x were a number, and you write 5 minus x plus x square. 3 plus 2 is 5. With that we have written minus x and we have added x square. And here again we are treating these symbols, this minus, plus, etc. as ordinary operations. But that is not how we are approaching the thing right now. Okay, truly in a polynomial x is not a number. It is related to something, an expression where x can be thought of as a number, but that will come afterwards, after we work out all the, after we define everything in this set and it turns out to be a ring, then only after some time we are going to do something called evaluating a polynomial at a field element. When we do that, then x can be thought of as a field element, but that is something that has not come yet. For us now, this is an abstract symbol. So the way we have always done these calculations, that is not justified. We have to properly define them. Now mathematicians always want to find things or want to define things based on what we already know or what we already have. It's like you have some things and using those things only you are creating new things. You don't want to bring some unfamiliar new thing from outside. But this set of symbols is bringing an unfamiliar new thing from outside. To rectify that, there is a way of defining polynomials using sequences, which I have discussed in my Facebook page. There I have discussed how polynomials can be defined as sequences of field elements. We are not going to take that view here. That's what Herstein has said. We could have avoided the phrase set of all symbols, and the motivation for avoiding the phrase is to make it more rigorous, because if you just simply say set of symbols, it becomes vague. We are bringing something from outside, so we have to make new rules so that the new things adjust well with whatever we have in our system. Instead of that, we could have defined polynomials by an appropriate apparatus of sequences. However, the current approach, in which we just think of them as some symbols, is good enough for us to do algebra. However, it's not the perfect way. The perfect way is to define polynomials using sequences. Okay, so that's why we are saying the current approach to call fx a set of symbols seems more familiar to most of us, because that's how we have learned about polynomials, no? As some symbols like this. We don't think of polynomial as a sequence. In fact, if you really have come across that interpretation, you have no doubt seen that thinking of a polynomial as a sequence, although it's logically perfect and in fact looks quite nice, but practically if you think of a polynomial as a sequence, you will confuse yourselves more. Okay, you will confuse yourself more. So that's the meaning of this part. In short, we continue to think of polynomials as some symbols which involve this x. However, keep in mind that now x is not a number. So this is just a symbol, and the total symbol has a meaning. Its individual parts, we don't attach any separate meaning to the individual parts. Okay. Now we are going to start our journey by first of all defining equality in this set, what it means for two polynomials to be equal. And the definition has been given like this: if Px equals a0 plus a1x plus etc. amx to the power m, and qx is equal to b0 plus b1x etc. bnx to the power n are elements in fx. Then we define Px is to be equal to Qx if and only if the corresponding coefficients are equal, that is ai is equal to bi for all I greater than or equal to 0, that is for all non-negative integers I. Now at this point I should perhaps mention one more thing. Note that this m and n need not be equal. In fact, the two polynomials that we saw previously, 3 minus x, and say let us take another one, 2 plus x square. In the first polynomial, the m is 1 because this is x to the power 1. That is the largest exponent. If you call that exponent this number, then that is the largest exponent that's appearing. Here in the second one, n is 2. Here this is the largest exponent appearing. So when we are saying that I is for all I greater than or equal to 0, what do we really mean? For example, here what is a0? a0 is 3. Here b0 is 2. They are not equal. Okay, fine. So this condition is not true when I is equal to 0 for these two polynomials. What about a1 and b1? a1 is minus 1 and b1 is 0. They are also not equal. Okay, fine. What about a2 and b2? b2, according to this notation, b2 is 1 because that is the coefficient of x square. But what about a2? You would say that there is no a2 according to this notation, because since m is 1, the polynomial stops here. We have from a0 to am. We don't have am plus 1, am plus 2, etc. But actually we have. That's a point that is to be understood here. Actually we have, and we have in this sense. What about a2? You can write the polynomial like this. 3 minus x can be written as 3 minus x plus 0x square, and 2 plus x of course is 2 plus 0x plus, oh no, sorry, what am I writing? 2 plus x square. Okay, so now these conditions or these equations make sense. 3 and 2, this is a naught, this is b naught, they are not equal. a1 is minus 1, b1 is 0, they are not equal. a2 is 0, b2 is 1, they are also not equal. But do we really have more I? Because here we have not, the way we have written this condition, it does not seem that I ends. We have just simply said that for all I greater than or equal to 0. Look at this, for all I greater than or equal to 0. That means for all non-negative integers. But what about a3 and b3? Just like you have brought this new term, you also have all the other new terms with 0 coefficient, and in fact it goes on. You can think of a polynomial in that way also. Just like that, here also so the condition that has been laid out here, actually that condition is to be true for all non-negative integers I. Here the condition has failed for I equal to 0, I equal to 1 and I equal to 2. However, for the higher values of I, the condition is true. All the coefficients are equal, in fact all of them are 0. In this sense, if you are interpreting a polynomial, you will see that every polynomial actually has infinitely many terms. If I want to call this a naught a term, a1x another term, as if this is a sum. This is not an actual sum because these symbols are not ordinary addition. However, if you just think of this expression as an abstract sum which has no value, then here there are not m plus 1 terms but actually infinitely many terms. The terms that you don't see, they are coming with coefficient 0. Here also we have infinitely many terms, and because a polynomial looks like an expression of this form where things seem to end, so that's why you can define a polynomial as an expression that looks like this. And the terms go on as if it's a series. Okay. However, only finitely many ai's are not equal to 0. Infinitely many, the non-zero coefficients will stop at some stage. If you consider an expression like this, say 1 plus x square etc., where all the coefficients are 1, then this expression is not a polynomial. Okay, in a polynomial it's also an expression of that form, but the number of non-zero coefficients should be finite. Here in this, the number of non-zero coefficients is 2. Here also the number of non-zero coefficients is 2. There should be a stage after which all the coefficients are 0. Now you understand the real meaning of this equality. Once you interpret the polynomials in that series form, all the corresponding coefficients should be equal. Then only we say that the polynomials are equal. Okay. Although the author hasn't explicitly said anything about these aspects, but he assumes that we know about them already, or at least we should be able to guess. So that's what equality of two polynomials means. Okay, next we come to the definition of addition. If the beginning is same, we have to consider two polynomials a1x etc. plus amx to the power m and qx is equal to b0 plus b1x plus etc. plus bnx to the power n are in fx, then we define px plus qx to be equal to c0 plus c1x etc. plus, actually he has written ct, but then he hasn't said anything about t. It just, okay, we will try to understand what t is. This where ci is defined to be equal to ai plus bi for all I. So he has written somewhat vaguely. Let's take this example itself. 3 minus x, that this is your px, and 2 minus or 2 plus x square, that is qx. So you express this polynomial, you make both the polynomials have the same number of terms. In our interpretation is infinite. Only finitely many terms are non-negative. Not non-negative, non-zero. However, those terms will matter. So if you are working with only these terms, then you have to, after adding, you will get another polynomial whose coefficients are the sums of the corresponding coefficients in the given polynomials. So here a0 is 3, b0 is 2. So c0 will be a0 plus b0. So that is 5. a1 is minus 1, b1 is 0. So c1 will be minus 1 plus 0, that is minus 1. So that is minus x. a2 is 0, b2 is 1. So c2 is 0 plus 1, that is 1. But even if you consider infinitely many terms where the others have 0 coefficients, they also will continue to give you the higher cn's for higher and higher values of n, or ci for higher and higher values of y. Say, if you, for example, want to calculate c3, then a3 will come after this as coefficient of x cube in the first polynomial, that is 0, and b3 likewise here is also 0. So c3 is 0. After that c4 is also 0. So that's why we don't write those parts. Okay, so for all I means still for all non-negative integers I. Simply put, you just, if you find these things difficult, you just think of the polynomial as a series, both the polynomials, and then add the corresponding coefficients. After you find the expression for the sum as a series of its own, you then collect the important part where non-zero coefficients occur and neglect the part where zero coefficients occur. Okay, so that's how we have to calculate sum, and you can see that with this new interpretation also we get the same answer as if we are doing high school calculation or school level calculation, and we are not thinking of these things as symbols or anything, but rather as thinking of x as a number. Okay, so that is addition, and then here they have provided one example. Let's just show you that example also. For instance, 1 plus x plus 3 minus 2x plus x square. So we make the first polynomial look like the second one, and then we have the second one also. So this becomes equal to 1 plus 3 is 4, 1 minus 2 is minus 1, so minus x, 0 plus 1 is 1. So that's how we can carry out addition. Next definition is multiplication. This is much more complicated than addition. If px is equal to a naught plus o, I said I will interpret this t. Do you see what t will be from this example or from the previous one that we had here? T is we cannot say the largest one. T is an integer that is less than or equal to the largest exponent that is appearing. In this case, the largest exponent among the two polynomials is 2, and the sum continues to have that 2. However, that is not necessary. Why I say will be at most that and not equal to that. For that you can consider this example. 1 plus x minus x square plus x square. So this is your px and this is your qx. The sum is 1 plus x. So you can see that although 2 is the largest one which appears in both the polynomials, but the sum has 1 which is smaller than 2. The thing is that this t is less than or equal to the maximum of m and n. Here m is 1, n is 2, so the maximum is 2, and t also turns out to be 2. Here m and n are both equal to 2, so the maximum is 2, but t is less than 2. The general case is that t will be less than or equal to the maximum of m and n. Okay, next we are going to define multiplication of two polynomials. Plus a m x to the power m and qx equal to b naught plus b1x plus bnx to the power n are in fx, then then we define their product to be equal to a polynomial c naught plus c1x plus etc. Okay, this time they have taken k. You can take anything where ci, now the expression for ci is a little difficult, I mean more difficult than the expression for ci in addition, and the expression ct they have taken a naught b t plus a1 b t minus 1 plus a2 b t minus 2. It will go like this. So you can see that the suffix of a1 ai is increasing, a naught a1 by 1 every time, 0 1 2 etc. Correspondingly the suffixes of the b's are decreasing by 1, so that the sum of the suffixes is equal to this suffix t. 0 plus t is t, 1 plus t minus 1 is t, 2 plus t minus 2 is t. In that fashion we are having the terms in this sum. This, however, note that these are, since these all the ai's and bj's are field elements, so this is an ordinary sum in the field. Okay, unlike this sum where the addition has no separate meaning. We will attach some meaning to it, but afterwards. So it will progress like this. At some stage we will encounter a t minus 1 and b1. The suffix of b it continues to decrease and it will reach this stage b1, and correspondingly we have a t minus 1. After that a t b naught. So here it stops, because if we take bt a t plus 1, then to make the sum of the suffixes equal to t, we have to take b minus 1, but we don't have negative suffixes, so it starts here and stops here. That is the tth coefficient of x to the power t in the product. Okay, now we are going to explain this. Here they are not even saying anything about t. Now we are going to explain this, illustrate this with an example. Take px equal to, let us take the example they have taken. And qx equal to 2 plus x square plus x cube. Okay, now suppose we are going to calculate the product. So comparing them with the general expressions, we can see that here a naught is 1, a1 is also 1, a2 is minus 1, and a3, a4, a5, these all the other coefficients are 0. Then b naught is 2, b1 is 1, oh sorry, b1 is not 1. See, I have to be more careful. Here we have a naught, a1, a2. Here however x appears with coefficient 0, so b1 will be 0, b2 will be 1, and so is b3, b4, b5, b6, these all the other coefficients are equal to 0. So now we are going to calculate the coefficients Ci for the product of these two polynomials. Then what is C0? C0 can be only A0, B0. A0 is 1, B0 is 2, so 1 times 2 is 2. Okay. C1 is A0 B1 plus A1 B0. 0 increases by 1, it becomes 1, 1 decreases by 1, that becomes 0. So the sum ends here itself. A0 is 1, B1 is 0. So this term will be 0. A1 is 1 and B0 is 2. So this term is again 2. Okay. C2 is A0 B2 plus A1 B1 plus A2 B0. Note that the terms are increasing, going on increasing. Here we have only one term in the expression for C0. Here 2 terms, here 3 terms. Okay. A0 is 1, B2 is 1, so this is 1 plus A1 is 1, B1 is 0, so that is 0 plus A2 is minus 1, okay, times B0 is 2. So this is minus 2 plus 1, that is equal to minus 1. Then we come to C3, A0 B3 plus A1 B2 plus A2 B1 plus A3 B0. So the number of terms in CT will be T plus 1 more than T. Here we have 0, so we have 1 term. For 1 we have 2 terms, for 2 we have 3 terms, and for 3 we have 4 terms. So this becomes equal to, we are going through this particular example just for the sake of practice and to really see how to calculate a product of 2 polynomials by the definition that we have been given. And then we will discover that after finding the product, we will see that we get the same answer as the one that we would calculate using school method, which is just basically taking the 2 polynomials and multiplying out the terms without thinking of anything, because you already have the algorithm in your brain. So C3 is what? A0 B3. A0 is 1, B3 is 1. So the first term is 1. A1 is 1, B2 is 1. So the second term is also 1. A2 is minus 1, B1 is 0. So this will have no effect. A3 is 0. So this term is also 0. So this is again equal to 2. And C4, we will continue calculating as long as we are getting non-zero coefficients, non-zero Ci's. A0 B4 plus A1 B3 plus A2 B2 plus A3 B1 plus A4 B0. Okay, A0 B4. B4 is 0, so the first term is 0. A1 B3. A1 is 1, B3 is 1, so the second term is 1. Then A2 B2. A2 is minus 1, B2 is 1, so this is minus 1. Okay, A3 B1. A3 is 0, so this will be 0, and since A4 is 0, this will also be 0, so C4 is 0. C5 A0 B5 plus A1 B4 plus A2 B3 plus A3 B2 plus A4 B1 plus A5 B0. Okay, you can see that in spite of having more and more terms in the expression for Ci as I increases, the calculation will become easier and easier. Why? B4, B5 are 0, so the first two terms are 0. Just like that, A3, A4 and A5 are 0. So this one and this one are also 0. And we only have to look at A2, B3. A2 is minus 1 and B3 is 1. So this is minus 1. What about C6? A0, B6 plus A1 B5 plus A2 B4 plus A3 B3 plus A4 B2 plus A5 B1 plus A6 B0. B starts becoming 0 from 4. So B6 is 0, B5 is 0, B4 is 0. A starts becoming 0 from 3. So this is 0, this is 0, this is 0 and this is 0 because of all the A3, A4, A5, A6 etc. This is equal to 0. And if you continue the calculation by not actually doing them but thinking of them, you will see that all the Ci's with higher values of i's will become 0. So by our definition, the product of these two polynomials 1 plus x minus x square and 2 plus x square plus x cube is equal to C0 is 2, so 2, C1 is 2x, C2 is minus 1, minus x square, C3 is 2 plus 2x cube, C4 is 0, so that will not be there, C5 is minus 1, so minus x to the power 5, and the higher coefficients are all 0. So this is the product. Now if you do it high school style, what will you get? 1 times 2 is 2, 1 times x square minus 2 times x square gives you minus x square. What about x? 2 times x is 2x. There is no other way of producing x. What about x cube? You will get x cube in two different ways. One is multiplying 1 with x cube, so that gives us 1 x cube, and the other x cube is multiplying x with x square, so that gives us another x cube. So x cube plus x cube is 2x cube, and we won't have x to the power 4, because minus x square times x square is minus x to the power 4, and x times x cube is plus x to the power 4, so they cancel out, so there is no x to the power 4. And for x to the power 5 you just multiply these two, so you get this one. So you see that our definition of multiplication of polynomials is actually nothing but the high school definition presented in a slightly more rigorous manner. The end result is same. In the high school definition we are simply multiplying without thinking of anything, as if these are numbers, because here we are treating x as number, but in our interpretation that we cannot do. So here we are not, ignore that we are not doing anything with x or anything with this plus signs. All we are doing is that we are calculating the coefficients, then using the coefficients we are again writing another such symbol. Okay, now having defined equality, addition and multiplication in fx, we are now ready to state the fact that fx forms a ring with respect to these operations, which however needs a proof, but we are not going to prove it, it's left to you. I have already seen that all the ring axioms are true for this addition and multiplication in fx for any field f. So it's up to you to convince yourself either by proving the axioms logically from scratch, or somehow convincing yourself even with examples that the axioms are always true, all the distributive laws, associativity of addition, multiplication, all those things. And the author has written like this: without any further ado, we state that fx is a ring with respect to the addition and multiplication defined. Its multiplication is commutative and the ring has a unit element. That is, it's not only a ring with respect to those operations, the set of polynomials, but it's in fact a commutative ring with unit element. Okay. Now next we are going to define something very important, namely the degree of a non-zero polynomial, and the definition goes like this: for a polynomial px, they have taken f. We can take px, but let's just take fx. Let's take what they have taken: a0 plus a1x plus an x to the power n, it's given to be a non-zero polynomial, that is all the coefficients are not 0. Oh, one more thing about the statement that fx is a ring is this: addition is there, multiplication is there. So what are the things you need to show that fx is a ring? You need to show that addition is commutative, addition is associative, there exists a zero element, and that zero element is the polynomial all of whose coefficients are 0. That's what we also call the zero polynomial over f. And for every polynomial we should have an additive inverse, which you can clearly see from the definition of addition, that it will be the, for these polynomials, say the additive inverse will be the one where in place of these coefficients we take their negatives in the field. If you add them you get the zero polynomial. Okay, then you have to prove multiplication is commutative, multiplication is associative. Okay, next there is a unit element. That unit element is the polynomial whose first coefficient is 1 and all the other coefficients are 0. Fine. What else? You need distributive laws to be true. Since the polynomial is, since the multiplication has been proved commutative, once you do that, only one distributive law is enough. The other follows from that and commutativity. So you prove that. So that proves that fx is a commutative ring with unit element. So it's this zero polynomial that we are talking about here. Our given polynomial is not equal to 0. In fx, where an is not equal to 0, we define the degree of fx written like this: deg fx to be the integer n. That is, if you have a non-zero polynomial, then the degree of the polynomial is the largest integer n, such that the coefficient of x to the power n is non-zero. For example, the polynomials that we saw previously, for example, you see here the degree of the first one is 2, because that is the largest integer, such that the corresponding term has coefficient -1, which is non-zero. The degree is not 1, because 1 is not the largest term. 1 is not the largest exponent, which gives us the term having non-zero coefficient. There is a bigger one. But 3 is not the degree, because coefficient of x cube is 0, coefficient of x to the power 4 is 0. The fact that a polynomial is an expression that looks like a series like that, which has only finitely many non-zero coefficients excuse me, that fact allows us to define degree, because then only we get a largest exponent for which the corresponding term has non-zero coefficient. So that is the degree. Here the degree is 3. That is, the degree of a non-zero polynomial note that this definition will not work if the polynomial is allowed to be equal to the zero polynomial, because there we will not have any non-zero coefficient, all the coefficients are zero. So that is the degree of a non-zero polynomial is the largest integer I such that the coefficient of x to the power I is non-zero. We do not define the degree of the zero polynomial. Some authors define the degree of the zero polynomial to be -1 or -infinity, or in fact any negative integer, but we will not do that. Some also don't define the degree of zero polynomial at all. So that's the convention we are going to follow here. For us, the zero polynomial has no degree, no concept of degree associated with it. Any polynomial of degree 0 is called constant. That is, constant polynomials are like this. All the field elements give us constant polynomials. There, the largest integer x, largest integer I, for which x to the power I has non-zero coefficient, is 0. After that, all the coefficients are zero. So such polynomials are called constants, and you can clearly understand why it's called constant, because it looks in our way of writing things somewhat less rigorously. In place of this, we would simply write 1, so it looks like a constant. So that's why they are called constant polynomials. They are polynomials of degree 0. Okay. Now our main aim is to show that eventually this fx is not only a commutative ring with unit element, but much more. It's in fact an integral domain, and even more than that, it's a Euclidean ring. Now you already know that to prove that a ring is a Euclidean ring, first of all it has to be an integral domain. Then there should be a function we have called d function, which should map every non-zero element of the integral domain onto the set of non-negative integers, such that it has properties. One such property is that d of a should be less than or equal to D of AB for all non-zero elements A and B in the integral domain R. The second property is like the division algorithm. It says that if we have two elements A and B in R, where B is not equal to 0, then there exist elements T and R in R such that A is equal to TB plus R, where either R is equal to 0 or the D value of R is less than the D value of B. If these conditions are true, then we say that R is a Euclidean ring with that D function. Now we want to show that Fx is a Euclidean ring, and we will see that degree of a non-zero polynomial will turn out to be ultimately the D function that we need in this ring to make it a Euclidean ring. You can already see some properties. We have defined degree of only non-zero polynomials, just like we define D function for only non-zero elements in a Euclidean ring. Also, the value of the D function, the values it has or it takes, must be non-negative integers, and you can see that degrees, the way we have defined, are in fact non-negative integers. The degree of any non-zero polynomial is ultimately a non-negative integer. So we now need these two things. We need to show this as well as the second thing to prove that Fx is a Euclidean ring. Once we prove that Fx is a Euclidean ring, we will then be able to apply all the results that we proved in the section of Euclidean rings to this particular Euclidean ring, and this gives us some very pretty non-trivial results, I mean in this particular case. Okay, so now I will go through so the results come after this. I think I should stop the video here. We have got a pretty good idea of what polynomials are from our perspective as some formal abstract symbols that can be added and multiplied, and it turns out that if we even don't think of them as abstract symbols and treat them as something that we already saw, I mean we have been seeing throughout our mathematical education, then the operations give us the same results. Okay, and we have also stated without proof that under these operations Fx forms a commutative ring with unit element. Now next step is we want to show that Fx is an integral domain and then a Euclidean ring, and then we will state all the results of a Euclidean ring in this particular Euclidean ring. So that part we will continue in the next video. So with this I end this video and see you in the next video. If you have any doubts about these things, then you can let me know in the comment section below. So signing off, have a nice night.